Hello, everyone. Hope everyone is having a great day. I'm Michael McClellan with L3 Levine Electronics and Electrics. Welcome to another one of our COVID-19 lunchtime webinars. Thank you so much for joining us. Today is a webcast, so your phones are muted, but we would love for you to ask questions. We love questions. Let's make this as interactive as possible. There's an icon, I believe, on the left side of your screen where you can click that and type in a question, and we will try to answer it at the end of the webinar. There are some handouts for you that I have attached, and you can download those now and take a look at them, and maybe they'll generate some questions. We are very lucky today to have a special guest. His name is Rick Wolf. I've known Rick for quite a while, and Rick and I have done some really neat things together. I met Rick in an interesting time in the transformer industry when ABB virtually had a monopoly on the cast coil transformer marketplace. And Rick and I were able to take some steps and penetrate that market, and had a lot of fun in doing so. So Rick is I wouldn't call Rick an American hero. He's not on CNN very often, but he's a hero within the transformer industry, especially within the cast coil transformer industry. So I'm going to turn it over to Rick Wolf, Vice President of JST Power Systems.
Thank you, Michael. Non-time related greetings to everybody in attendance today. And Michael, I didn't think American heroes ever showed up on CNN. I better be careful. Anyway, as Michael said, my name's Rick Wolf. I'm Vice President of Business Development for JST Power Equipment. And today I will talk about our epoxy transformers. And I know the presentation title was History of Cast Epoxy Resin Transformers, but I'm really going to talk a little bit more about the evolution, what led up to the cast epoxy resin transformers, and what applications they're suited for, and so forth. So without further ado, let me get into it, and we'll start with the objectives. And Michael, is all this control panel stuff visible, or
No,
I just
sir.
see my.
No,
It
sir.
is?
You're the only one that sees it. The audience does not see that.
Good. Okay. Just so the audience knows, I have controls. I even have zapper buttons so I could cut you out. No, I'm only kidding. But I just want to make sure that the clutter doesn't mess up the presentation. So here's my objectives today. I'm going to start, as I said, with the evolution of transformers, and basically explain why it was desirous to come up with dry type solutions to certain problems. That's going to be followed by a discussion of dry type transformers and a comparison between those. And we're going to end that with epoxy cast resin transformers. And I'll follow that with a discussion on applications for the cast epoxy resin. We'll talk about the fabrication of cast resin transformers. And I'll give you a little bit of info on our company as it relates to the cast resin transformers. And this will be followed by a Q&A session to answer any of your questions. This presentation wanted to run faster than I could. Anyway, so basically, we started with oil-filled transformers, and the reason you have oil-filled transformers is, especially in power applications, because in power you dissipate heat. And it's no mystery that one of the best ways to dissipate heat, I should say, there's a lot of the losses that give off heat. You want to dissipate it, and one of the best ways to dissipate it is with a liquid medium. It's very good for taking the heat away from the transformer windings. So in any type of power applications, you basically had oil-filled transformers, but there were certain problems there in that they were high maintenance. You had things like transformer fires, and they could contaminate the atmosphere. So it was always desirous to use dry type transformers, which they had, but they were usually in small non-power applications, because they wouldn't have the same environmental problems that the oil type had. And so we entered a cycle in trying to develop dry type transformers. And if you look at how the dry type transformers evolved, there was always an effort into increase the mechanical strength, and more importantly, the insulation systems with the dielectric properties. You wanted to try to, as close as possible, get the same type of performance that you were getting with the oil filled. So they started with basically the open wound. It was an open frame, dipped and baked. It was dipped in a vat of varnish and baked. The problem there was you had a lot of air bubbles, there were voids, and so that basically weakened your insulation system. And that led them to look at other methods. One was using vacuum pressure to help get rid of some of the voids in the varnish, and you had a process called VPI, for vacuum pressure impregnated, and that did just that. It enabled you to produce a dry type transformer with some better dielectric properties, and that was followed with VPE, vacuum pressure encapsulated, which is basically a few extra dip processes to give you a thicker outer shell on the transformer, followed by an actual encapsulation process that is epoxy coating or something that is the shell of this VPI transformer. And last on the evolutionary scale was cast coil transformers that were basically windings that were cast in a mold and sealed in a solid block of epoxy. So when we compare the dye type transformers, there's obviously, like everything else, advantages and disadvantages of each. With VPI and VPE, the main advantage is that you do have now a dry type transformer, so it's environmentally friendly, and it's basically lower cost. The disadvantages, and this is relative to epoxy cast resin, you still have weaker dielectric properties that specifically manifest itself with partial discharge and VIL. They're less efficient in that they run hotter, and when you have harsh environments that may be prone to contaminants, they don't really perform as well either. Cast coil, on the other hand, has advantages that basically are opposite of some of the disadvantages that I just presented with the VPI. They both are environmentally friendly in that they're dry type transformers. They do have good dielectric properties, so you can realize relatively high VIL ratings. They're very good with partial discharge. And being that it's cast in a solid blocks of epoxy, it's basically impervious to a lot of the contaminants, and you have superior mechanical strength with that, that shows up when you're looking at electrical faults and things, which we will discuss. The main disadvantage there is that it has a relatively higher purchase price. So with what we just talked about in evolution, I want to just go over an applications guide and just see in certain applications where these things fit. So with oil fill, you're able to use those in both high voltage and medium voltage applications. And that's important to point out because you get to a point, especially with high voltage, and it all really boils down to the current. You have your I square R losses, and as a result, you get to a point where you cannot use any type of air-cooled system to take away the heat that's dissipated from your I square R losses. You have to use some type of a liquid to do that. So there are certain applications because of that where it has to be an oil-filled transformer that's being used. Oil-filled transformers basically have good dielectric properties and they run cool. So if your application requires a high dielectric strength, high BIL levels, you can use the oil filled. It also runs cooler than any type of dry type. Again, that should be intuitive because you're using liquid to cool as the medium that's cooling. If you are concerned with the environment, which you may be in some urban area where things are on top of each other, then you may not want to use an oil-filled transformer because it is more, it's not environmentally friendly type of equipment. It's less prone to resist damage from short circuits and faults because there's really nothing holding the windings. When you have these types of surges, because all transformers are involved with magnetics, you have a lot of buildup of forces. Some of these forces are immense, and they can do damage to the windings and even the structure of transformers. And oil fill does suffer from that. VPI and VPE, again, they are dry type, so you're able to use those in environments where it will be environmentally friendly. So if you take applications that are in an urban atmosphere, densely populated, you don't really want to pollute it, VPI and VPA would fit that application. They're not suited for harsh environments, so if you have a lot of contaminants in the air, they can get in where the windings are, and it's more difficult to clean than a cast epoxy resin transformer, and that eventually would lead to discharge. They also have poor dielectric properties, so your dielectric withstanding voltage, your BIL, and your discharge will, if those are critical, and you have certain specified levels in that application, you may not be able to use those transformers. They do run hotter than the cast and oil filled. Obviously, as I said, that is the coolest type of transformer. But when you get to dry type, they do run hotter than the cast. The mechanical strength too is less likely to resist the damage of strong electrical surges and short circuits. We end with the cast coil. That gives you the best combination of electrical and mechanical factors. You're able to use those in medium voltage applications, and in a lot of cases, a lot higher voltage levels than you would use the VPI. Typically, we use these a lot in 35 kV class applications. They do have good dielectric properties associated with the insulation system. And they are perfect for harsh environments because, again, it's an impervious shell that's protecting the windings. They do run hotter than the oil filled, but much better than the VPI. And just to give you an example, typical temperature rise specs for VPI are 150 degrees C. In cast, there's two standards that are out there. There's an 80 degrees C and 115 degrees C. And it really depends on the application and cost targets for the particular project. They are very reliable with respect to their construction. They resist damage with heavy electrical surges, short circuits. I've witnessed several short circuit tests, and what usually is considered a destructive tester, there's going to be a certain level of repairs after for both oil filled and VPI. For cast, those units undergo the testing and then it's shipped to the final application as well. It's with no repairs needed. Okay, so I'm going to shift gears a little bit and talk specifically about cast resin and the construction. I need to shuffle some things around on my control panel so I could see this. Okay, now I could see. And I'm not sure you could see my mouse, but I'm circling it around a cross section of the windings. That's actually a coil that was cross section. So you could see that the windings are fairly uniform and they're embedded in epoxy. And we will talk about how those are fabricated because there is other insulation just outside of the epoxy in there. But typically these are rigidly bound in epoxy in a vacuum casting process. As I pointed out, the cast resin are higher on the evolutionary scale of transformer technology in that they were designed at a point where they were trying to get dry types to have a better insulation system. And basically, you have two coils that are arranged coaxially around the iron core. When we look at some of the product advantages, why use cast? As I pointed out, they're typically more expensive, so why use them? First of all, the reliability. It's considered a high reliability type transformer. They have lower installation costs, especially when you're comparing it with liquid filled, because there's no contaminants, there's nothing extra in the construction phase that you need to do with these, similar to the things that you would do with a liquid filled transformer. And they're safe and environmentally friendly. They're not giving out any contaminants either. The reliability, they're rigidly bound and sealed windings, and what that gives you, it's less prone to the effects of contaminants and particulate matter in the atmosphere, and especially with VPI, that could be a bad situation for VPI transformers. It's basically intended, you look at some of the environments, and I'll show you later a list of installations, subway stations that are prone to brake dust and other contaminants, factories and processing plants where they have particulate matter in the air. Those are the types of environments where a shell that's impervious to particulate matter definitely is advantageous for the application. Their design life is over 25 years. I see a lot of spec with 20 years, 25 years, and Our company's been in existence since 1993, and we still have transformers of that vintage in service today without any issues. The mechanical strength versus the liquid filled and VPI, as I said, if there's short circuits, that strength lets you overcome a short circuit without any mechanical damage. They're not prone to some of the problems I say with circulating fluids. Not all liquid fields have anything circulating. It's basically the heat that will help circulate the fluids. But there's a lot of problems with the fluids. They have to be checked, and they get, again, some chemicals in the fluids over time where you actually have to change it. And this gets into more of a maintenance thing. And there's little risk of shutting down. Another important factor is the installation and cost of ownership. And this is specifically the advantage of dry type over liquid filled. When you look at the site preparation, there's no precautions against the flammable substances. And even a lot of the oils that they use now for the liquid fills, they're not flammable, but it's still considered a contaminant. So from a construction perspective, you need to build in catch basins. It has to be, the room has to be a certain size and so forth. Also, one of the things you could do with the dry type, you can close couple those to switchgear, saving space. And, you know, I know again in dense urban populated areas, space savings could be a big thing, especially with some of the real estate costs that you see in some of these urban areas. There's limited maintenance. You don't have to do the inspection of the oil. Like I said, with liquid filled, there's periodic inspections to do a chemical analysis on the oil, and there's no changing of seals or anything of that sort. For cast, they're higher efficiency, so they're low losses. We typically see efficiencies 99 point whatever percent. We meet the most of your eco standards, which are basically in Europe, but your Department of Energy standards in the US as well. There's better cooling with respect to what you would see with a VPI, and that just has to do with the way you're able to keep the windings uniform, and you know, some of the fillers in the epoxy that are a pretty good heat conductor. There's lower decommissioning cost in that when you do have to decommission it, you don't have anything that's considered hazardous that you're getting rid of, and their operating life is extremely well, is probably better than any type of transformer out there.
Hey, Rick, let me jump in here. It's Michael. Just to speak to the reliability standpoint, you know, I do spend quite a few hours each month quoting dry type transformers to replace VPI transformers that have failed in the field. And so it's a fairly common thing after 10 or 15 years, especially if the environment is not pristine. You know, the particulate matter, like in a paper mill or especially some sort of steel mill, it just gets in between the paper insulation layers, and then it's only a matter of time.
Right. That's exactly, and that's why I showed the application guide. I mean, I'll show an application guide, but the big thing and the problem I think with the world these days is everybody considers CapEx and not OpEx. So they make the judgment, well, we'll go with the VPI, and they will try to use it in a harsh environment. But eventually the contaminants, as you do say, get trapped in the BPI insulation system, and it will cause discharge. And discharge over time will wear down your insulation system till it eventually fails. And so what do they say? You know, I forget what commercial it was, pay me now or pay me later. It's that type of thing. So when you look at OpEx, there's really nothing better than the cast resin, and you do get the long life out of it for sure. And as Michael was just mentioning, is when you look at it's safe and environmentally friendly. It's used in some of the most pristine environments, college campuses, hospitals. There's, you know, any place where you would not want any fear of something that could possibly contaminate. There's no flammable liquids, so that's a reduction in fire hazards. And again, if you look at your decommissioning costs and waste disposal, you don't have the concerns you do with liquid fill. One of the things that we've done, there was a time where these were real old liquid fill transformers with PCBs, and they want to replace those. They actually were replacing those with cast resin transformers, and that a lot was with concerns of transformer fires, things like that. You don't have those concerns with the cast epoxy resin. Here's some of the applications that would utilize cast epoxy resin transformers. It's basically large-scale construction and infrastructure projects. So in urban development, that will be your trains, subway stations, airports, transportation hubs, hospitals, office buildings, as I pointed out, to college campuses, commercial development, factories, processing plants, and computer data centers. Computer data centers more because of the reliability. They also run cooler. As Michael just pointed out, with factories and processing, paper mills is a perfect example. These are all typical applications where you see a cast epoxy resin transformer specified. In electrical power generations, they're excellent for the excitation and isolation transformers for the gas and steam turbines, as well as the main step-up transformer used in wind energy. In fact, wind has probably become the biggest part of our business today. This gives you some of the installations that our company has done to give you a flavor for the application. So there was a data center in Virginia where there were 4 3,750 kVA transformers. ThyssenKrupp steel mill in Alabama, and that was a number of transformers. I forget, I mean, it was north of 30. Michael, you remember that one? Is that correct? I think it was north of 30 transformers we supplied on that, right?
Yeah, no. So there were 115 transformers.
Jesus, that's well north. And that was a combination of 2, 3, 4, 5 MVA. There was a lot of transformers on that.
Yeah, let me jump in. I want to say something about that site. That's been a very interesting few years. We furnished all of the cast coil transformers that were used in the distribution system. A competitor provided cast coil transformers that were used on the process side of things, where some rectification and that kind of thing was involved. I believe they were feeding drive system, maybe even some SCR heaters. And over and over and over again, we have replaced our competitors' units. I wish Adam was on the phone. To the tune of about 1 or 2 per year. And of course, to be fair, I'm not going to mention the competitor's name, but we have replaced those units, and that just goes to show that casting a winding is not a simple endeavor. There's not an instruction manual that comes with the epoxy that we purchase from 3M or different vendors. It is an art form that has to be mastered over many years, and JST has done that, and as a result, our coils have never cracked. But down at that site, just north of Mobile, Alabama, our competitors' units continue to fail, about one per year.
Thanks, Michael. The other was a hospital at an Air Force base, 1500 kVA. There's a Con Edison repowering station on the East River in New York. There's a 3000 kVA there. The CTA, Chicago Transit Authority, their subway systems. We have rectifier transformers in their red line and brown line. And then for SEPTA in Pennsylvania, they're also a sublay application, but these are for substations and not rectification. In Grand Central Terminal in New York, we have transformers. Procter and Gamble, we basically in several plants, we have transformers again, and that's one of your processing plants. When we look at large scale projects, you'll see cast coil transformers in these large scale projects as well. And the one that we're fairly proud of was the New York City World Trade Center project. And again, as I said, when you're looking at densely populated urban areas, I think New York City qualifies for that. And so you do see in that area a lot of use of epoxy cast resin transformers. But for the World Trade Center, there was a transportation hub. It was used for the temporary power, for the chiller plants, for the memorial, and the path, which is a rectification. The path is actually a subway system that runs between Manhattan and New Jersey under the Hudson River. So now I'd like to shift gears a little bit and show you how these are actually manufactured. We'll start with the coil winding. And Michael, I don't know, does my mouse show up on the screen as I'm going through this? Oh, I guess I lost Michael. I hope it does, because I'm trying to point out things. But we basically start with wire that's wrapped with the electrical crepe paper that has certain absorptive properties, and it's wound on a mandrel, as you could see here.
Hey Rick, go to the drawing tools. If you want to point, if you want to point something out,
yeah,
there's a tool.
In my control panel.
Yes.
I see a drawings tool menu. Let's click on it. Pen, highlighter, spotlight. Oh, look at that.
Yeah,
you see the spotlight? All right, that's a beautiful thing. So again, we have this wire that we've actually made this wire ourselves. We buy the raw extrusion and draw it through a die. But so, oh, the mouse shows up. I have a shill out in the audience, by the way. His name's Mark Lucina. Some of you in attendance may get to know him later on, but he just texted me and said the mouse shows up. So I'm very happy for that. So I could definitely point out, I got a lot of tools now to point out what I'm trying to point out. But we do manufacture our own wire. We get the extrusions, draw it through a die, and then we wrap it with a special grade crepe paper that we specify for its absorptive properties. That's wrapped on a mandrel, and there's a lot of tension controls, again, to keep the right uniformity and integrity that we're going to need for the winding. You'll also see where I'm pointing out now that there's kind of a sheen. That's actually a fiber mat insulation that gives you your layer to layer insulation. But when all is said and done, you will end up with this coil that's dropped on the inner part of a mold, and then there will be an outer shell that's put around these for casting. When you look at the LV coils, it's a lot of it's the same, but instead of wire, we're actually using foil. Okay, now can I turn this tool off? No.
Hey, Rick, do we cast both the primary and secondary?
Yes, we do.
You want to comment on the folks that don't?
Well, a lot of people don't. They use a pre-preg, which is, when I say pre-preg, it's epoxy sheet. It looks like these fruit roll-ups. They actually roll it with the foil, and that goes into an oven and it's cured. So when we say pre-preg, it's epoxy resin that already has the hardener in it, and when you subject it to heat, it cures. It's not, we do that process too. I don't sell a lot of it in the US because it just doesn't give you the integrity like a fully cast secondary would. But close pen color. So Michael, how do I turn this off? Is there any way to turn this off, Michael?
Try pressing escape.
Thank you. There. Okay. Oops. Casting. I got the slides mixed up. That's actually in our repair and maintenance section. And that's what our repair and maintenance people spend a lot of time doing, that type of casting. Now, obviously, I'm only kidding. That is Ron Ara, who's a surf casting champion that lives up in the Cape Cod Canal area. But this is the type of casting we're talking about. So again, this is vacuum casted in these, and let me, well, I already, Mark texted me and said the mouse shows up, so I'm just going to use the mouse. These are the vacuum casting chambers. There's an oil diffusion pump that basically gets it. I forget how many atmospheres, but it draws a pretty good vacuum. And we then mix epoxy, as you see here. There's a lot of controls with it. And then we're going to pour it into the molds that are in this casting chamber. There's two types of mixing processes. There's a static and a dynamic mixing process. The difference being a dynamic is your typical batch mixing where you take the resin and hardener all at once, mix the batch, and then pour it into the mold. There's the static where you're actually mixing it at the same time it's being injected into the mold. And that's a little bit more expensive as far as equipment, but it's really the way to go. You get a much more uniform casting. That's the method that we implore. And as you see, there's a lot of controls with casting.
Let me jump in here. It's Michael. So Rick mentioned uniform casting. That's an extremely important term because if the casting is non-uniform, the resin does not shrink and expand uniformly as the conductors shrink and expand as more current runs through them and they heat up. And that is what causes coils to crack.
Okay, core cutting. Basically, I think they call the geometry we're after when we build the core cruciform. I'm not really sure what that ever meant, but what we want to do, it's a round core. So we basically buy the steel directly from the mill, and we're going to slit it into different widths. And so the idea is that if you take a series of different widths and you start on the bottom with a narrow one and slowly build up to the middle with wider widths, and then start to stack with narrower widths, you eventually get a round form. So that's basically the idea of the different widths. And here you see we have a turret, and there's multiple turrets with different widths, and they will cut the laminates. Now, the other thing we need to do is, because they're miter joints, we need to step lap it so it's step lapped and mitered to really reduce the noise that you would get, and that's actually audible noise. So what the machine does, and it's all computer controlled, it will select a certain width, and then it will cut off a series of laminates, each one a little bit shorter, and then it starts all over again until you're done with that width, and then it switches to the next width and starts over again. And so eventually you build your core structure that's round in geometry and has the step lap mitered construction that you would need. And right in the middle here is a finished core ready for assembly, and the bottom's held together with what we call core clamps. These are stacking tables. As you can see in the background here are the multiple turrets. This is where they're stamped, and it's fed onto this stacking table that does everything automatically till you build your core logs. Okay, final assembly and test is simply marrying the coils that we casted onto the cores, and that's what you see happening here. And then eventually, once you have the coils on, you put on your top yoke. And typically these would then be installed in some type of enclosure, depending on an application. Some people buy it without the enclosure because they're going to put it in an e-house with other equipment. But then they're all tested. Now, there's a series of routine and design tests that you would do. This test console that you see here is set up for doing a lot of the routine tests, and this test stand you see here is an impulse test, which is one of the design tests. Typically, your design tests are sound level, heat run, and impulse. Also short circuit, but it's very rarely done if you've done it on similar size transformers, because it's a very costly test to do. Okay, that's basically it for the technical information on cast resin transformers. I'm going to talk a little bit about our company. This is the commercial part, but I am going to keep it simple and not a lot of corporate motherhood. But we recently moved to a new headquarters from Carlsbad, New Jersey, to Lake Mary, Florida. The company is JST Power Equipment. We have 4 manufacturing locations in China that, and I focus on this first because all of our casting is done there. I don't have any casting chambers in North America, but it started in Haikou, we were operational since 1993, and we started with cast epoxy resin transformers. We do other types of electrical equipment now, but our start was cast epoxy resin transformers. And there was a reason for that. In China, the building codes are such that any building with public access has to be epoxy cast resin. So you're looking at over $1 billion industry in China alone, and we're the largest supplier there. There's a factory in Wuhan, and it's not just known for the coronavirus. And actually, you come to, we have a factory. You see the size of the factory. I will say this: that not a single one of our employees from that factory it got the virus. So go figure. But that basically supplies the domestic market in China. So that $1 billion+ market I told you there, all that comes out of this factory. There's a factory in Shanghai, and actually they do VPI products there. And that really does not do a lot of cast, actually any cast at all. But then we have a state-of-the-art factory in Guilin, and they do a lot of our standard cast transformers there, as well as some of the transformers that are imported. We basically service North America out of our factory in Mexico. They basically import the coils that are casted so that we get the coils from our factories in China. But that's a 60,000 square foot facility that does the core cutting and final assembly. There's a lot of capabilities there. That's a picture of it from the outside. Again, you'll see a similar core cutting setup, similar to what I just showed you in the other pictures. They do have a paint booth and a lot of other equipment that they use in the manufacturing of these transformers. This is final assembly, and it's again an operation like I just showed you, where coils are lowered on to the core to married up, and then the top yoke would be assembled. And we have all the full test capabilities there too. So he's in a test room, and outside there's all the whether it's design or routine test, we do it all. Plus the warehousing that goes along with that facility. So basically that's it. In summary, cast epoxy resins were developed to provide a better reliability, longer life, lower cost of ownership, and be much better than in the environment. I left out again it's the insulation system. The dielectric properties of our insulation system are really the best that you could get for any dry type transformer. Our company, we use state-of-the-art engineering processes and equipment to produce those epoxy cast resin transformers. And we offer a lot of advantages over others in the areas of service and technical expertise. And we're basically very familiar with the needs you would have to meet the applications that are out there. And with that said, I'd like to thank you all for participating. And I guess we could open it up for questions.
Okay, great. Question came in. Could you do a zigzag secondary winding?
Simple answer, yes.
Okay, great. Can you comply with Buy America?
Yes.
Yeah, I know that one. We've been through that. Gosh.
We did it.
Yeah.
Before we moved to Lake Mary, we had a factory, which I didn't show. I showed the Lake Mary factory in Carlstadt, New Jersey. And I sourced a lot of things locally. Again, at a minimum, I have to import the coils.
Yeah, I remember when we went through this, Rick, and it was quite an exercise, but it ended up that Buy American is really just an exercise in accounting. A certain amount of money has to come from manufacturers located in the States. So if I remember correctly, you guys casted the coils in China, and then you had the enclosure fabricated in the States. You guys did the final assembly in the States. You tested it in the States, and all
I
that.
could even buy cores in the States. But
Oh, right.
but the thing now is anything with the Americas comes out of Mexico. Now Mexico is doesn't meet Buy America because it's Mexico. But
Well, it meets under the NAFTA agreement.
yeah,
We'll send out an email. We'll send out an email on that.
yeah,
Another question
it really doesn't. But I still have manufacturing capability in the U.S. when we need. So the short answer is yes, we can meet Buy America.
Yeah. Okay, a question came in. Is there any difference in the temperature ratings of a cast resin transformer when compared to a VPI transformer?
Yes. Okay. So basically, all transformers are specified with the temperature rise, and also, and this is a question I get a lot. They say, oh, okay, well the varnish type transformer VPI, that's a 220-degree insulation system, so that's better than cast. You only have 180, and that's not really the way to look at it. Every transformer has a temperature rise above ambient. And as I said, in cast, there's typically two standards that are used. There's an 80-degree rise and 115-degree rise. Now, if you look at what, and in the US, it's IEEE ANSI, they usually throw in allowance for the hot spot. So basically, you have a hot spot somewhere when you're doing a temperature rise test. You're taking what they call the average rise through winding resistance. And so it's average, but you know somewhere there's a hot spot, and the ANSI standard allows you allowance, and it's 30 degrees. Now, because of some of the uniformity I showed you for the cast resin, you don't get that delta in the hot spot. We may be 10 degrees, 15 degrees, it's not 30 degrees, but we still use the standard. And so what does that mean? Well, you have a rating on your insulation system, and let's say class H, 180 degrees. So that means I have to take my ambient, I add to it the specified rise I'm allowed, say 80 degrees, and the allowance for the hot spot, which is 30. So if I'm in a 40-degree ambient, I'm 70 degrees right there, I add 80. That combination has to be below 180 degrees, which it is. Same thing when you look at 115-degree rise. For VPI, you're 220 degrees on the insulation system, but it runs hotter. So typically you see temperature rise, they're spec'd at 150 degrees, and the same argument applies. You need to take the ambient plus the hot, and really that allowance developed by IEEE, the 30 degrees, was really developed because of VPI. And that 30 degrees is probably closer to what you really get with the VPI. But having said that, your life of the transformer really, if you believe in what people like UL tell you, is your ability to run cooler than the rating of your insulation system. So if you're not running to full load, and you're not even heating up the transformer, let's say to 80 degrees, you're running maybe somewhere like 70. Your life, you're going to use the transformer forever because of just the way you're operating. There's a lot of headroom between the rating of the insulation system and what you're running it at. Hopefully that answers the question.
Yes, it does. Here's a good question. With cast coil transformers, how do you draw out the tap connections?
It's yeah, it's really easy. They have, and I didn't show it in the coil winding process. You basically have points where there's certain turns where you have a lead that's welded right to that wire, and then you have all the insulation that goes out of it. So at the end, basically, before they put it in the mold, you have this coil that's been round with a bunch of these little, they look like dongles hanging off it. That's all fixtured in the mold, so it's all molded together, but they form your taps.
Yeah, we can send some pictures out of that. It's done virtually the same way as a dry type. So,
Yeah.
Okay, I'll take this one. How competitively priced is JST cast resin transformer compared to US manufacturers? So this is an interesting question, and it's changed dramatically over the last, say, 10 years. When Rick and I first started doing this in the US, boy, we came in like 35, 40% less than the US manufacturer because there was only one. There was only one manufacturer, and when that happens, you don't necessarily get the most competitive pricing. So against the American manufacturer, we were way, way less. And we were only asking about a 10 to 15% premium over a VPI transformer. I think that margin has narrowed even further in the last 10 years. There have been some other competitors that have jumped into the market. JST and others have gotten more efficient in how they're building transformers, and so the gap continues to narrow. And so we see more and more specifications for cast coil, just because if it's only a 10 or 15% premium, I mean, it's a no-brainer. I hope that answers the question. Here's another question. How does a cast resin transformer hold up in marine applications or applications that are close to the ocean or maybe have salt air?
Again, it holds up very well. We've built things for marine applications. These are enclosed, so there's certain requirements that come in with the enclosure. But in general, it's an impervious shell of epoxy that seals the windings. You don't get much better than that. What you really need to protect is the connection points. And that's why you have these enclosures that are basically sealed. There will be a heat exchanger and some type of cooling liquid like water. They will be water cooled. The enclosures will be something like that. But that's in our enclosure design. So we will do that. But when you look at the insulation system, in and of itself, it's superior to any type of contaminant, whether it's salt or what have you, than any other type of transformer there is. Well, especially VPI. So the answer is very well.
Okay, final question. I think we're about out of time. You mentioned that the cast epoxy resin offers better dielectric properties than either the VPI or VPE transformers. Can you describe this in quantitative terms?
Sure. And it's really simple. If you look at, let's take BIL. You really see this in BIL and partial discharge. But cast epoxy resin transformers, we will use those in applications where you have a 200 kV BIL specified. And even then, your primary may not even be 35 kV class. It may be lower, 15 kVA class, but they'll have a 200 kV BIL spec. We're able to do that with cast epoxy. PD, and again, the lower the level, the better. We're able to realize below 10 picocoulombs. In fact, most of your specs request that 10 picocoulombs or below. Now compare that to VPI. VPI, you will not typically see it spec in where you're above 100 kV BIL. And basically I see partial discharge specifications for VPI anywhere from 50 to 100 picocoulombs. As I mentioned, we do VPI, and once you get below 100 picocoulombs, we now have to look at that very hard because it gets tougher to do with the VPI. So that just gives you kind of a quantitative. If you're up, you know, if you have a high BIL, like I said, over 100 kV, some 200, 150. But specifically with discharge, if you're going to be around the 10 picocoulomb level, it has to be cast. You're not going to do that. You're probably off by a factor of 10 or so with VPI. Hopefully that answers it. And if not,
Great.
My email address is up on the screen, post it there. If I haven't answered your question, please send me an email and I'll do my best to answer if I know the answer.
There's actually a typo on the screen. Rick's email is RWOLFF.
Oh, all right.
JST-The.com. Yeah. And so we were out of time, unfortunately. This was a great session because of you all in the audience. We got some great questions and we're able to have a very good dialogue. If you asked a question and we didn't get to it, I apologize, and we will send you an email answering your question. Hope to see you at another L3 Levine webinar soon. Take care.
By the way, my email address is right now. That's a joke. It is right though. I just fixed it.
Take care. Have a wonderful afternoon.